3i Atlas took 3 massive hits, and the results are truly shocking. Welcome back to the Deep Dive. You joined us today because we're plunging deep into a truly confounding astronomical event, the bizarre saga of 3i Atlas, the third confirmed visitor to our solar system from interstellar space. This tiny object, a cosmic interloper, just experienced, well, a trio of direct, devastating solar attacks in late 2025, right near its closest approach to the sun. But the core mystery, the one that has, every planetary scientist buzzing, is that the object, according to the initial analysis anyway, it didn't even flinch.
That's exactly our mission today.
Right.
We've got this stack of source material articles, notes, transcripts, detailing the timing, the trajectory of this whole event,
Right.
where this little object was apparently blasted by 3 massive coronal mass ejections, CMEs, from the sun. So our task is really to move past maybe the sensational headlines and unpack the precise observational data, look at the competing scientific hypotheses, because they are competing fiercely right now, trying to explain this impossible stability of 3i Atlas. Why did its orbit just stay perfectly predictable, despite taking hits that, well, by all known physics, should have absolutely knocked it off course?
Absolutely. And before we dive into the solar fireworks and the potentially new physics involved, which is fascinating stuff,
It really is.
we need to establish a baseline, a comprehensive one. We need to know exactly what kind of thing 3i Atlas was before all the drama kicked off.
Yeah, that context is critical. The initial data already painted a picture of, well, an extreme traveler, you could say.
Extreme how?
Well, 3i Atlas was discovered relatively recently, July 1st, 2025, spotted by the ATLES telescope survey down in Chile.
Okay.
But within days, literally days of discovery, the trajectory calculations made astronomers basically drop everything else they were working on.
Okay, let's unpack this trajectory data specifically, because most things we track, comets, asteroids, they're stuck here gravitationally.
Right, bound to the sun.
This one was anything but.
Precisely. It became obvious very quickly this wasn't some standard long-period solar system body just looping back. Its path through space was traced as a hyperbola. That's the unmistakable mathematical signature of an escape curve.
Meaning it came from outside.
Exactly. It originated outside our system, it's just passing through, and it's on its way back out to interstellar space. But what sets 3i Atlas apart, even from the other interstellar visitors we've seen?
Like Oumuamua and Borisov.
Right, it's the sheer extremity of its orbit.
How extreme are we talking? Give us some context on that hyperbolic signature.
Okay, so when we talk about orbital shape, we use eccentricity. Anything above 1.0 means the object is unbound, it's escaping.
Right.
Now, some of the longest period comets from way out in the Oort cloud might get close, maybe 0.9999.
Almost escaping, but not quite.
Exactly. Oumuamua, the first one, that was about 1.2. Borisov, the second, was maybe 3.4.
Okay.
3i Atlas, the calculations put it between 6.1 and 6.2.
6.1, that's huge.
It's absurdly hyperbolic. It means it's not just escaping, it has a tremendous amount of excess speed. Kinetic energy way beyond what our sun's gravity can really slow down or capture.
And that excess speed, that translates directly into velocity, right?
Yeah.
What kind of speed are we talking about relative to the sun?
It's traveling at roughly 60 kilometers per second, relative to the sun's rest frame.
60 kilometers a second.
Yeah, I mean, put that in human terms.
Right.
Over 134,000 miles per hour. It's just a terrifyingly fast breakneck speed.
Wow.
And crucially, it's going to maintain almost all of that speed as it leaves our solar system. The velocity, the orbital shape, it all strongly suggests it came from way out, probably the galactic thick disk.
The thick disks, so potentially very old.
Very old. Could have been wandering for billions of years.
Okay, so we have this incredibly fast ancient visitor. Now let's get a sense of its size and what it looked like as it got closer to the sun.
Right. So perihelion, its closest approach to the sun that was calculated for late October 2025.
Just recently, then.
Exactly. This pass brought it just inside Mars's orbit. About 1.35 astronomical units, so maybe 200 million kilometers from the sun.
Close enough to get interesting, but not a sun grazer.
No, definitely not. Close enough to be warmed up significantly by the sun's radiation, trigger some activity, but yeah, safely far enough away.
And we got a good look at it physically, using our best tools.
We did. Observations from the Hubble Space Telescope back in July 2025, they confirmed it had that classic cometary look.
Meaning?
A small, solid nucleus inside, surrounded by this halo of gas and dust that's the coma. And then a tail being pushed away by the solar wind and radiation pressure.
Okay, and the size?
Based on standard models, how bright it looked, the nucleus was estimated to be surprisingly small, only about 2.8 kilometers in diameter.
2.8 kilometers. That is small for something traveling that far that fast.
It is. But, the size wasn't the biggest shock. It was the chemical makeup. That's where the James Webb Space Telescope, the JWST, came in.
Ah, the composition data.
Exactly. JWST used spectroscopy. It basically analyzed the light coming from the coma to figure out what molecules were actually vaporizing off the surface.
What did it find?
Highly unusual results. The coma was overwhelmingly dominated by carbon dioxide, CO2.
CO2, not water.
Not water, which is usually the main component for our solar system comets, whether they're from the Oort cloud or the Kuiper belt, or even carbon monoxide, CO2.
Right.
This was just loads of CO2.
What does that tell us? Why is that so strange?
Well, it implies a completely different thermal history, a different chemical environment where it formed. CO2 sublimates, turns from ice straight to gas at much colder temperatures than water ice.
Okay.
So its dominance could mean a few things. Maybe it formed in an extremely cold, very carbon-rich environment in its home system.
Right.
Or maybe its long billion-year journey through space has thermally processed it. Maybe the more volatile ices like nitrogen or CO got stripped away gradually, leaving CO2 as the main thing vaporizing now that it's near our sun.
Either way, it flagged it as chemically.
Absolutely.
Yeah.
Right away, it told us 3I Atlas wasn't playing by our solar system's chemical rules.
Okay, so let's recap the baseline. Small, maybe 2.8 kilometers, hyperfast, 60 kilometers, CO2-rich coma, wildly hyperbolic path, eccentricity over 6.
Yep.
And crucially, up until the moment it passed behind the sun, its behavior was completely by the book.
That baseline of predictability is absolutely essential to understanding the anomaly that follows. Because in early October 2025, just before perihelion, it made a close pass by Mars.
Okay.
And spacecraft like the ExoMars Trace Gas Orbiter, they were able to observe it. And up till that point, the object showed precisely 0 deviation.
Zero.
Its position, its velocity, it all lined up perfectly with predictions based just on Keplerian mechanics, the gravity of the sun and the planets, no weird forces needed.
Perfect predictability, rock-solid orbit.
Exactly. And then it dipped behind the star, and everything seems to have changed. Or rather, didn't change when it should have.
Right. This is where the story takes that genuinely mysterious turn. Mid-October, 3I Atlas goes into superior conjunction, passes directly behind the sun from our viewpoint.
Yep, and you can't track anything that close to the sun with normal optical telescopes. The glare is just overwhelming.
So you need special tools.
This is where the coronagraphs come in. These are basically big space telescopes designed specifically to block out the main disk of the sun.
Create an artificial eclipse.
Exactly. They use what's called an occulting disk. This lets scientists see the incredibly faint stuff right next to the sun, like the corona, the solar atmosphere, satellites like GOES 19, OSOHIO, the stereo twins, they all carry these.
And people watch this data, right? Independent observers.
Constantly. There are researchers, citizen scientists who sift through this public coronagraph data all the time. And they did report faint detections. They tracked 3I Atlas, frame by frame, apparently just dutifully following its predicted path right through the sun's glare.
Okay, so it was tracked even behind the sun. But while it was in there, in that hostile environment, the sun apparently decided to unload.
That's what the report started saying. The sources talk about the solar cannonade. The data logs from solar weather observatories, the coronagraphs themselves, they confirmed it. 3 massive coronal mass ejections, CMEs, launched in rapid succession, all within about 48 hours.
3 of them.
3 huge ones. And here's the absolute kicker, the critical alignment. These blasts came from highly active regions on the far side of the sun.
Far side, meaning they weren't aimed at Earth?
Correct. They were primarily directed away from us, so they didn't cause big geomagnetic storms here, didn't make the headlines maybe.
Their trajectory must have lined up with 3I Atlas.
Exactly. The timing, the spatial trajectory, it seems they aligned perfectly with the calculated position of 3I Atlas right when it was near perihelion, its closest approach, getting maximum solar heating.
Okay, we need to pause here. A CME. What exactly is that hitting the object? It's not just light, right?
Oh, absolutely not. You need to visualize this. It's like a billion-ton wave of magnetized solar plasma.
Plasma. Super hot gas.
Gas so hot the electrons are stripped from the atoms. And this mass gets ejected from the corona at incredible speeds, hundreds, maybe even thousands of kilometers per second in these cases. It carries immense kinetic energy and powerful tangled magnetic fields.
Okay, so Physics 101. What should happen when a billion tons of fast-moving plasma hits a tiny 2.8-kilometer icy nucleus?
Basic Newtonian physics, right.
Yeah.
Laws of momentum, force. A direct hit from even one of these CMEs should do several things. Physically, it should strip away a lot of the comet's coma, the gas cloud. It should compress the tail. And most importantly, it absolutely has to transfer kinetic momentum to the nucleus itself. A push.
Non-gravitational acceleration, like we saw with Oumuamua, but caused by a direct hit.
Precisely. Even if the transfer isn't perfectly efficient because the object's small, a measurable force must have been imparted.
Can we quantify that? If it took those hits, how much should it have budged? What kind of deviation are we talking about?
Okay, based on models of how CME energy couples with a small nucleus, maybe 2.8 kilometers, made of ice and dust, a direct impact should have caused a velocity change, maybe on the order of 20 meters per second, possibly more, depending on the CME density.
20 meters per second. That sounds tiny compared to its 60 kilometers per second speed.
It sounds tiny, but here's why it matters enormously in orbital mechanics. That 20 meters change isn't just a one-off blip. It accumulates.
Ah, because orbits are so precise.
Exquisitely precise. So over the days and weeks it took for 3I Atlas to move away from the sun, come out of conjunction, and become visible again to regular telescopes. That 20 meters per second velocity error compounds. It adds up.
Into a positional error.
Into a substantial positional shift. By the time we could see it clearly again, we'd expect it to be thousands, maybe tens of thousands of kilometers away from where the original unhit ephemeris predicted it should be.
And that's an error we can definitely spot.
Oh, easily. Definitive. Ground-based telescopes tracking it weeks later would see that discrepancy immediately. No question.
So, recap. 3 massive CME impacts. Perfect alignment, physics says. Expect a noticeable deflection, a change in orbit. The result.
The result, according to these initial analyses of the coronagraph data and subsequent tracking, was stunning silence. The object that emerged from behind the sun was apparently exactly frame by frame where the pre-CME ephemeris predicted it should be.
No deflection.
No measurable positional deviation. No detectable change in velocity. No change in direction. It just kept going, as if the solar cannonade, those billion-ton blasts, had simply passed right through it like a ghost, imparting zero momentum.
Okay, that doesn't make sense.
That is the core mystery. That's the contradiction we need to solve.
All right. If basic physics, momentum transfer, says it has to budge, but the observational data, even this preliminary data, says it didn't, we have a major problem. A cosmic scale contradiction.
We do.
Let's unpack the possible explanations. We have to start with the conventional ones, right? Ways scientists try to make this fit without, throwing out Newton.
Right. You always start by assuming maybe your initial parameters were wrong or there was some coincidence. The first, and maybe simplest, is the near-miss idea.
Okay.
The nucleus of 3I Atlas is tiny, remember. 2.8 kilometers. CMEs are enormous structures, but they aren't uniform. Their density, and therefore the momentum they carry, varies dramatically within the cloud.
So maybe the densest parts just missed.
It's plausible, though maybe improbable, that the 3 densest momentum-carrying cores of these CMEs simply happen to miss that tiny solid nucleus. Maybe they just passed through the very diffuse, almost empty outer coma without transferring significant force to the core itself.
But 3 near misses in a row, when the alignment was described as perfect, that feels like really stretching statistical luck.
It does feel like a stretch. Which brings us to the second conventional idea. Maybe we got the object's inertia wrong. Maybe it has a higher density than we assumed.
Meaning it's much heavier for its size?
Exactly. If the nucleus isn't fluffy ice and dust, what if it's much more massive? Dense rock, maybe even metallic. If it's far heavier, its inertia would be much greater. It would resist being pushed.
Okay, that makes sense from a physics standpoint. More mass, harder to move.
Right. That 20 meters impulse from the CME might become, say, an undetectable 2 meters impulse against a much denser core.
But wait, doesn't that fly in the face of what we saw? The coma.
Ah, you've hit the central problem with that theory. Yes, it absolutely does. A really dense, rocky core, or a chunk of metal, typically doesn't produce a massive, highly active cone rich in CO2 like 3I Atlas clearly had.
Right, you need volatile ices near the surface to get that outgassing.
Precisely. The very existence of that active coma strongly suggests a lower density body, where those volatiles can easily escape when warmed by the sun. And that kind of body should be easily pushed by CMEs.
So it forces a contradiction.
Yeah.
The density needed to resist the push contradicts the composition needed to explain the coma we observed.
Exactly. You can't easily have both. based on our current understanding of comets and asteroids.
Okay, strike two for conventional explanations, maybe? What's the third? Cosmic luck again? Cancellation.
This one relies on incredibly precise and arguably unlikely geometry. The cancellation hypothesis suggests that the momentum vectors, from the three CMEs somehow manage to partially or even fully cancel each other out.
How would that work?
Imagine, just hypothetically, the first CME hits and pushes it slightly up and left. The second CME hits shortly after, pushing it down and right by just the right amount. And maybe the third gives it a final tiny nudge back onto its original path.
So the net effect is zero deflection.
Mathematically, yes, it's possible. But achieving that kind of perfect cancellation from three separate, massive, inherently chaotic, non-uniform solar eruptions
Seems incredibly unlikely.
It's statistically improbable to the point of almost being absurd. It requires a truly bizarre, coincidental alignment of forces and timing.
Okay, so if the conventional physics explanations lead us to contradictions or, astronomical levels of coincidence, we have to at least entertain the alternative, the truly mind-bending one.
The exotic hypothesis.
Yeah. This is the idea that maybe 3I Atlas isn't just a passive victim here. Maybe it's forcing us to rewrite some rules about how stars and small bodies interact.
This hypothesis suggests that 3I Atlas isn't just passively drifting through the solar wind. It might be actively, dynamically interacting with the sun's magnetic field and the plasma environment around it.
Creating some kind of feedback loop or a short circuit.
Potentially. Something that fundamentally changes how momentum gets exchanged between the CME and the object.
Okay, let's break this down. There seem to be two key parts to this exotic idea. First, how it might trigger the CMEs aimed at itself.
Right. The proposed trigger mechanism hinges heavily on that immense speed, the 60 kilometers per second.
Right.
When something moves that fast through the sun's magnetic field lines, which are everywhere in the inner solar system, it cuts through those lines very powerfully.
Like a wire moving through a magnetic field in a generator.
Exactly like that. According to Faraday's law of induction, this rapid motion through the magnetic field induces strong electric currents in the surrounding environment.
And the coma is key here.
Yes, because the coma of 3I Atlas isn't just neutral gas. It's already ionized by sunlight. It's a plasma. And specifically, a CO2 plasma, which might have unique conductive properties. So these induced currents could be significant within that plasma cloud.
And how does inducing a current lead to a massive solar eruption like a CME?
The theory goes that this electrical and magnetic disturbance, created by the object's fast passage, acts like a catalyst or an anomaly within the sun's corona itself. It might trigger a sudden violent release of stored magnetic energy that's already built up in the active regions on the sun.
That's called magnetic reconnection.
It's the process, magnetic reconnection. So the hypothesis suggests the object isn't just hit by chance. It essentially causes the sun to fire CMEs back along its own path. It becomes an active player, perturbing the local solar environment.
Wow. Okay, if it somehow triggers the blast aimed right at it, it needs a heck of a defense mechanism to survive with no effect. That's the second part, the shielding idea.
Precisely. If it triggers the attack, it needs a perfect shield. And the theory suggests the same electromagnetic coupling provides that shield.
How?
Those electric currents, induced in the conductive CO2 plasma coma, now interacting dynamically with the powerful magnetic fields carried within the incoming CME itself, could create a sort of magnetic cushion or shield.
A magnetic shield made of plasma.
Essentially, yes.
Yeah.
This invokes something called the Lorentz force. That's the force magnetic field exerts on moving charged particles, like the ions in the coma plasma and the CME plasma.
Okay.
In this scenario, the Lorentz force would act to redistribute the CME's incoming momentum. Instead of the momentum being transferred kinetically like a billiard ball hitting another ball, it gets transferred and redirected electromagnetically through magnetic pressure acting on the plasma envelope surrounding the nucleus.
So the force hits the plasma sheath, gets deflected or absorbed magnetically, and the solid core inside is untouched.
That's the idea. The CME impacts the plasma cloud, but the force is magnetically shunted around the solid nucleus, leaving its trajectory completely unchanged.
That sounds like something out of science fiction.
It does, but it draws heavily on real physics, specifically the work of Hannes Alfvén, the Nobel laureate who pioneered magnetohydrodynamics, or MHD.
MHD, the study of magnetic fluids, basically.
Right. Alfvén argued for decades that electromagnetic forces play a vastly larger, often overlooked role in cosmic plasmas than simple Newtonian gravity and momentum usually account for. This 3I Atlas scenario could be a prime example. If this shielding mechanism is real, it would fundamentally change our models of plasma physics, especially how small bodies interact with stars.
It employs a whole new layer of interaction we haven't accounted for.
It really does. A potentially profound one.
Okay, to really get our heads around how weird 3I Atlas is or might be, we need context. We've had other interstellar visitors. They weren't exactly normal either.
That's a key point. Interstellar objects seem to have a track record of being outliers. They force us to confront the diversity out there in the galaxy.
Let's start with the first one, the really famous one Oumuamua back in 2017.
Right. Oumuamua really set the benchmark for weirdness, didn't it? It was only just unbound eccentricity 1.2, but its shape was bizarre, very elongated, maybe cigar-like, maybe pancake-like.
And no coma.
Critically, yes, no visible coma or tail, unlike a typical comet. Yet, as it flew away from the sun, it showed this unexplained non-gravitational acceleration. It was speeding up, just slightly, beyond what gravity alone could explain.
Which, without a visible coma, led to some wild theories.
Extremely wild. Everything from it being made of exotic stuff like solid nitrogen ice, which could sublimate without much visible dust, to the really controversial idea that it might be an artificial light sail.
Okay, so that was visitor number 1. Weird shape, no coma, weird acceleration. Then came visitor number 2, 2I Borisov in 2019.
Borisov felt almost conventional by comparison, strangely enough. Its eccentricity was higher, about 3.4, so definitely interstellar.
But it looked like a comet.
It really did. It had a clear coma, mostly water-rich apparently, a distinct tail. And crucially, its non-gravitational acceleration, the slight push it got, was perfectly explained by standard cometary outgassing models, just ice turning to gas, pushing it slightly.
So Borisov showed us that some interstellar objects might be chemically quite similar to our own comets.
Exactly. It suggested our little corner of the galaxy isn't entirely unique in how comets form.
And now, 3I Atlas, where does it fit in this hierarchy of weirdness?
Well, 3I Atlas takes things back towards the strange end of the spectrum. It's the fastest of the three, by far. It seems to have the largest nucleus, maybe 2-3 kilometers, and it has that unique CO2-dominated chemical signature.
So it's not like Oumuamua, no coma,
Like
not like Borisov, water-rich coma. It's his own kind of weird.
Precisely. It really reinforces this idea that maybe weird is normal for interstellar objects. They likely represent a vast population of material out there, maybe originating from places like the galactic thick disk, older regions of the galaxy with different chemistry. And this population is far more diverse than the relatively uniform sample we see originating within our own solar system.
Okay, let's challenge an assumption then. We keep calling it a comet because of the coma, but what if its resistance to being pushed by the CMEs points to something fundamentally different? What if it's not a comet nucleus as we know it?
That opens up some really fascinating possibilities, challenging its very nature. One idea is that it could be a fragment of an exoplanet.
Like a piece of a rocky planet from another star system.
Exactly. Imagine some cataclysmic event in another solar system, maybe a giant impact between planets, or a planet getting tidally ripped apart by its star. What if 3I Atlas is a chunk of the rocky or even metallic core that got ejected?
How would that explain the coma, though? Wouldn't a rock just be a rock?
Not necessarily. That core fragment could still have volatile materials like CO2 trapped deep inside, maybe locked within carbonate minerals, for example. Our sun's heat, as it got closer, might have been just enough to finally bake out that trapped CO2, creating the coma we saw.
And a dense, rocky core would explain the resistance to the CMEs.
Inherently, yes. If it's mostly rock or metal, its density would be much higher, giving it far more inertia. It would naturally resist deflection, potentially explaining the stability without needing exotic magnetic shields, though you'd still need to explain such an active CO2 coma from trapped volatiles.
Interesting. What about its age? You mentioned it might be billions of years old. Could that play a role?
It could. Maybe it's an ancient relic. What if it formed around a really early star, a population 2 star? These are stars with very low metallicity, formed when the universe was much younger and chemically simpler.
So it would carry chemical signatures from a different cosmic era?
Potentially, yes. Billions of years older than our sun. And that incredibly long journey wandering through interstellar space, being bombarded by cosmic rays, could have processed its surface and structure into something. Well, something we just haven't seen before, something unique.
There was also a mention of a magnetized core. How would that work?
This is a really intriguing idea. What if the nucleus isn't just rock or ice, but contains a highly conductive core, maybe iron-rich, that still holds some remnant magnetization from when and where it formed?
Like a tiny, weak magnet buried inside.
Sort of. Even a faint residual magnetic field generated by the nucleus itself, if it exists, could interact quite strongly with the highly magnetized plasma of a CME. It could provide an internal mechanism for that magnetic shielding effect we discussed.
Is there any evidence for that?
It's very speculative, but some reports mentioned unusual measurements of polarized light scattering off the coma. Polarization can sometimes give hints about magnetic fields, but it's complex to interpret. It's more of an indirect hint, supporting the possibility.
Wow. So, fragment of a planet, ancient relic, magnetized core. The implication here, regardless of the specifics, seems huge. Why should someone listening care about this, beyond just astronomers scratching their heads?
Because these interstellar objects are fundamentally geological archives of other star systems. They are essentially free samples delivered to our doorstep from entirely different cosmic environments.
Samples processed under different conditions than anything in our solar system.
Exactly. They carry the chemical fingerprints, the isotopic ratios, the structural clues from distant stellar nurseries, from planetary systems that might have formed completely differently from ours. They force us, scientifically and philosophically, to look beyond our own local, maybe even parochial sample set. They're expanding our understanding of how matter clumps together, how chemistry evolves, and how information gets carried across the sheer vastness of the galaxy.
Okay, let's pivot slightly here. We've discussed these amazing possibilities, but we need to ground ourselves in the reality of the data. Because the most sensational parts of this story, the confirmed CME hits, the absolute lack of deflection, the magnetic shielding, these are not yet established facts in peer-reviewed journals, are they?
That is the absolutely crucial caveat here. We're dealing with what you could call the hidden data problem, or maybe the data still under analysis problem. These claims, especially the non-deflection and the shielding hypothesis, are emerging largely from preliminary analyses, often by independent researchers digging through public archives, like the coronagraph data.
Which is valuable, but not the final word.
Not at all. It's a vital part of the scientific process, this open data analysis. But the really precise, carefully calibrated data needed to prove non-deflection and to definitively confirm the properties and exact impact geometry of those CMEs is likely still fragmented or being meticulously processed by the official mission teams associated with those spacecraft.
So what specific data points do we desperately need to nail down to turn this from a fascinating mystery into verifiable new physics, or even just a confirmed coincidence?
We need several key things. First, we absolutely need precise, high-cadence astrometry from those coronagraph images. That means detailed, frame-by-frame positional measurements of 3I Atlas as it moved behind the sun. This is hard. The data is noisy. The sun's glare is intense.
Okay, better positions. What else?
Second, ideally, we'd need in-situ plasma measurements. Data from spacecraft that were actually in the region at the time, like maybe the Parker Solar Probe or Mars orbiters, that could tell us the exact speed, density, and magnetic field strength of the specific CME plasma that would have hit 3I Atlas.
Ground truth for the impactor.
Exactly. And third, how do we even confirm the CMEs definitely originated on the far side and were aimed correctly, since we couldn't see them directly from Earth?
How do we know they were there?
We need sophisticated, correlated, far-side solar observations. This mainly comes from a technique called helioseismology. It's like using sound waves, seismic waves, traveling through the sun to map activity, like large active regions or explosions, on the side facing away from us.
So we need to cross-reference the timing and location from helioseismology with the object's predicted path.
Precisely. Only by confirming the CME source location and timing via helioseismology and matching that to the object's trajectory can we definitively say, yes, a collision was unavoidable and occurred at this time. Until all those pieces are published and verified, the collision remains inferred, even if it looks highly likely from the initial data.
And this uncertainty, this gap between the initial reports and the peer-reviewed confirmation, creates a vacuum. And nature, especially internet nature, abhors a vacuum.
Indeed. And that vacuum often gets filled with more speculative narratives. We need to address the space weather connection that seems to have gained some traction online.
Right. What's the claim being made there?
We've seen some sources suggesting a link. The idea is something like 3I Atlas might have triggered these CMEs. Okay? Those CMEs came from active regions on the sun. Those same active regions then rotate around to face Earth maybe a week or two later.
Right.
And the speculation then tries to tie potential upcoming solar flares from those regions aimed at Earth to various other terrestrial or near-Earth events. Sometimes a lunar phase, like a supermoon or a full moon, gets thrown into the mix, leading to predictions of heightened geomagnetic activity, maybe even increased seismic activity, earthquakes here on Earth.
Okay, we need to be absolutely crystal clear with listeners on this specific point. What's the scientific consensus?
The scientific consensus is unambiguous. Any narrative directly linking 3I Atlas's passage, the CMEs it encountered, subsequent Earth-directed solar activity, lunar phases, and terrestrial seismic events is extremely speculative and finds absolutely no support in mainstream established science.
Why do people make the connection then? Is it just seeing patterns?
Largely, yes. It's observing potentially simultaneous or sequential events and assuming a causal link where none is known to exist. We have to patiently explain why these connections are unfounded. Lunar phases influence tides? Yes. They have negligible, if any, proven effect on triggering major earthquakes or large CMEs.
And CMEs triggering earthquakes?
There's no established physical mechanism for that either. Geomagnetic storms from CMEs can induce currents in power lines, affect satellites, but they don't penetrate deep enough or carry the right kind of energy to trigger fault lines to slip. Conflating these things, mistaking correlation for causation, is a serious risk, especially when it fuels unfounded fears about natural disasters.
So it's crucial to separate the legitimate, verifiable solar threat from this unsupported speculation. What is the real documented danger from the sun right now?
The real threat is straightforward solar physics, and it is significant. We're in solar cycle 25, and it's proving to be stronger, more active than initially predicted.
We saw that earlier in 2025.
Exactly. We had some extreme X-class flares back in mid-2025. That kind of legitimate solar activity poses a direct, well-understood risk to our technological infrastructure. Power grids are vulnerable to induced currents, GPS accuracy can be degraded, communication satellites can be disrupted or damaged. That's the real space weather threat scientists are actively monitoring and preparing for, not some kind of comet-triggered earthquake synced with the moon.
Understood. So dealing with the real data challenges here, sifting through noisy coronagraph images, correlating far-side solar data, modeling complex plasma interactions, this sounds incredibly data-intensive. Where does technology like machine learning or AI fit in?
Oh, ML and AI are absolutely critical for making progress here, and in solar physics generally. Think about the sheer volume of data constantly streaming down from spacecraft like SOHO, Stereo, GOES, Solar Orbiter.
It's overwhelming for humans to process manually.
Completely. So algorithms are essential. Machine learning models can be trained to automatically detect faint objects, like 3I Atlas moving against the bright corona. They can classify the properties of CMEs, speed, density, morphology, far more rapidly and consistently than human analysts.
And can they help test the deflection mystery specifically?
Yes, significantly. ML models are perfect for running complex simulation loops. You can feed them the known physics, but vary all the uncertain parameters, the comet's exact density, the CME's precise impact point and energy, the efficiency of momentum transfer.
Run thousands of what-if scenarios.
Exactly. Simulate the interaction across the entire range of possibilities allowed by the error bars. This lets scientists rigorously test if any combination of conventional physics parameters, maybe a slightly higher density plus a glancing blow from the CMEs, could possibly explain the observed lack of deflection.
Or does the data truly demand something new?
Right. It allows a systematic way to determine if the data forces us towards that exotic short-circuit magnetic shielding hypothesis. It helps transform what might seem like speculation into a computationally verifiable, testable hypothesis based on the available, albeit messy, data. AML is key to extracting signal from noise here.
Okay, so the analysis is ongoing, complex, maybe aided by AI soon. But 3I Atlas itself isn't waiting around. It passed perihelion in late October 2025. The clock is ticking.
Absolutely. The urgency of observations is very real. The object is now moving rapidly outbound, heading back towards interstellar space, and as it gets further from the sun, it's going to fade exponentially.
Getting harder and harder to see.
Very quickly. So we have a narrow observational window right now.
Yeah.
The absolute top priority is continued post-perihelion astrometry. We need those high-precision positional measurements now that it's clear the sun's glare.
To see if that potential deflection, even if small, becomes noticeable over time.
Exactly. If that 20 meters per second nudge did happen back in October, the resulting positional error should be accumulating. It might be detectable now or in the coming weeks as a measurable difference between its actual location and the path predicted without any CME interaction. That's the smoking gun for deflection, or lack thereof.
What else do we need before it fades too much?
We desperately need more high-resolution imaging if possible, but even more importantly, detailed spectroscopy. We need to lock down the precise isotopic ratios in that CO2 coma.
Isotopes, like different weights of carbon and oxygen atoms.
Precisely. Measuring the ratio of, say, carbon-12 to carbon-13 or oxygen-16 to oxygen-18 gives you a unique chemical fingerprint. It tells you about the nuclear processes in the star or nebula where that material originally formed. That's crucial for tracing its origins.
And it's fascinating how that chemical fingerprint, the CO2 dominance, connects to other things we're finding out there.
It really is. That unusual CO2-rich composition aligns thematically, maybe surprisingly, with recent findings from JWST looking at exoplanet atmospheres. We're finding more and more exoplanets, particularly certain types, whose atmospheres seem to be dominated by carbon dioxide, not water vapor or nitrogen like Earth. It suggests that planetary formation environments, very different from our own solar system, maybe richer in carbon, might be quite common across the galaxy.
So 3I Atlas isn't just an oddball, it might be a sample of a common type of environment out there.
It could be. It reinforces this idea of it being a flying archive of extraterrestrial chemistry. It's carrying these precise chemical clues from a distant stellar nursery, potentially one that formed planets in a way totally unlike how Mars, Earth, and Venus formed.
And looking ahead, we're going to get more of these visitors, right? The detection rate is expected to go up.
Dramatically so. The Vera Rubin Observatory in Chile, when it comes fully online soon, is expected to increase the detection rate of interstellar objects hugely. From the one every few years we've had so far to potentially several per year.
Wow, so each new one will be a test case.
Exactly. Each new interstellar object will help us figure out, was 3I Atlas a truly bizarre, maybe magnetically active one-off anomaly? Or is it actually representative of a large, diverse, and often chemically weird population of interstellar travelers?
And is there any chance, however remote, of actually visiting one of these, like we did with Bennu or Ryugu?
It's incredibly difficult given their speeds and unpredictable arrival times. A rapid response mission would need to be ready to launch almost instantly and be extremely fast itself. It's technologically a huge challenge right now.
But the payoff.
The scientific payoff of getting a sample, even a tiny robotic sample return, from an object confirmed to be from another star system would be immense.
Yeah.
Revolutionary. It would give us the same kind of leap in understanding about other stars that the Bennu and Ryugu samples are giving us about the formation of our own solar system. It's the ultimate ground truth.
Okay, so wrapping up this deep dive into the enigma of 3I Atlas, it really leaves us facing this stark choice, doesn't it? A fundamental challenge to our models.
It seems so.
Either this object is far denser, far more massive than its size and active coma suggests, which is a deep paradox in itself, or it's somehow actively interacting with our sun's magnetic field electromagnetically in a way that genuinely requires a new chapter in plasma physics.
Yeah, suggesting maybe Newton's laws plus simple gas dynamics aren't quite the whole story when you have a highly conductive object blasting through a magnetized plasma at 60 kilometers per second.
Which is a profound thought.
My final analysis, I think, is that the most important lesson here, regardless of the eventual explanation, is that these interstellar objects, simply by being interstellar, inevitably force us to confront anomalies. They push us to expand our understanding beyond the limited, maybe even slightly parochial, sample of objects born and raised within our own solar system.
So whether the final answer is exotic new physics or just a really complex, hard-to-unravel combination of conventional effects.
Exactly. That intellectual confrontation with the unexpected, with data that doesn't quite fit. That's precisely how science advances. It pushes the frontiers. That's the real value here.
Okay, and here's a final provocative thought for you, our listener, to consider as we wrap up. If we can manage to measure those precise isotopic ratios of carbon and oxygen in 3I Atlas's CO2-rich coma before it fades completely, you know, the ratio of carbon-12 to carbon-13, oxygen-16 to oxygen-18, could we potentially use that unique chemical fingerprint? Could we use it to trace the object back, not just vaguely to interstellar space, but maybe to a specific type of stellar nursery, perhaps one known to have a distinct mass range or a particular metal content that might produce such isotopes?
A chemical return address.
Exactly. Could we pinpoint the kind of environment it was born in billions of years ago? We might literally be holding the chemical key to a distant birth recorded in that faint gas cloud, if only we can decode the signal before it vanishes back into the void.